Okay, welcome to the solution of the problems in magnetism. Some of these problems are just direct applications of the equations, while some others you really have to visualize and think. Question 1 talks about a 1.5 meter length of a conductor carrying 4.5 amperes of current, and it's oriented horizontally. And at that point on the Earth's surface, the dip angle of the Earth's magnetic field makes an angle of 38 degrees. Estimate the magnitude of the magnetic force on the wire due to the Earth's magnetic field, which is given. And now you need to know that the dip angle is the angle made by the horizontal component of the Earth's magnetic field with the actual magnetic field, which means that the Earth's magnetic field is not horizontal. But we are only interested in the horizontal component in this case because the wire is kept horizontally. So when you sketch a diagram, you're going to get something like this. You have the Earth's magnetic field, and the conductor is kept horizontally. And the angle between them is the dip angle, which is 38 degrees. So now that's the strength of the magnetic field. And the force acting is given by ILB sine theta. The current is 4.5 amperes, length is 1.5 meter, magnetic field is 5.5 times 10 to the negative 5 Tesla. Sine 38 gives you 2.6 times 10 to the negative 4 newtons. In this question, the force on a wire carrying 8.75 ampere is a maximum of 1.28 newtons when placed between the pole faces of a magnet. And if the pole faces are 55.5 centimeters in diameter, what's the approximate strength of the magnetic field? The most important word here is the force is a maximum. And the force on a conductor becomes maximum only when it is kept at right angles to the magnetic field. So that means the angle is 90 degrees between the current and the magnetic field. Another thing is that the length of the conductor is not given because it's immaterial. What is given is the diameter of the pole faces, and that should be taken as the length of the conductor because it's only on that part of the conductor that a force acts, because only that part is inside the magnetic field. And now therefore use the formula for maximum force, which is ILB, because sine 90 is 1. And then from there calculate the magnetic field strength. Now that's in meters. And you get 0.2635 Tesla. In this question, a 5 mega electron volt kinetic energy proton enters a 0.20 Tesla field in a perpendicular plane to the field. What is the radius of its path? You know that when a charged particle enters a magnetic field perpendicular to it, it's going to make a circular path. And the radius, whenever any object makes a circle or a circular path, a centripetal force acts on it. In this case, the centripetal force is equal to the force on the charged particle. So we have the formula for force on the particle, and we're going to use that. And centripetal force is mv squared by the radius, which will be equal to the force. But we need the velocity of the particle, which is not given directly. We need to find the velocity of the particle from the kinetic energy. So that's step number one. From the kinetic energy, find its velocity. Now, kinetic energy is given as, kinetic energy is of course 1/2 mv squared. So if you rearrange that, you're going to get velocity squared is 2k by m, or velocity is square root of that. But kinetic energy has to be in joules. Here it's given in mega electron volts, and a mega is 10 to the 6. So that's why you have 5 times 10 to the 6. And then to change electron volts into joules, you multiply with the charge of the electron. Okay, so first you change mega into electron volts and then change it into joules. This is the mass of the proton which will be given to you. And then once we get the velocity from here, we can use the concept that the centripetal force mv squared by r is equal to qvb. Now what is that? That is the formula for maximum force acting on a particle moving through a magnetic field. So rearrange that to make the radius the subject. You get mv by qb, and m is the mass of the proton, which will be given to you. And velocity is what we just found out, so I don't want to write that whole stuff again, so I've just, put an arrow there. Kind of lazy, And Q is the charge of the electron. And the magnetic field is 0.20. When you substitute all that, you get 1.8 meter. But by the by, you get the velocity as 3.1 times 10 to the 7. So that's the number that goes in there, okay? So that's now clear. And I think I made a calculation mistake, and I should get 1.62 meter. Brings us to the fourth one. And in this question, you have a doubly charged helium atom whose mass is given, and it's being accelerated by a voltage of 2100 volt. What will be its radius of curvature if it moves in a plane perpendicular to a given magnetic field? And again, what is its period of revolution? Now, this question is similar to the previous one. The only difference here is that the voltage through which it is accelerated is given. Now, by definition, if an electron is accelerated through 1 volt, it will have a kinetic energy of 1 electron volt. So to find the kinetic energy of the particle, all you got to do is multiply its charge with the voltage through which it is accelerated. Multiply its charge with the voltage. Now, the problem says this is a doubly charged helium atom. When it says doubly charged, that means it's lost both the electrons. So its charge is now twice that of the electron. Okay. So to find its kinetic energy, multiply its charge with the voltage. Now do be careful that you have this as the velocity and this is the voltage. So when you rearrange that, you get velocity in this format. And then again, we know that the centripetal force is equal to QVB as before, and from which you can find the radius. Same as the previous problem. Now what I did here is I just substituted this whole value of velocity in this place, okay? So that's why you see that there. And that is what I get if you look at it carefully. Therefore, now I can, there is a mass outside and there's mass under the square root, and that simplifies to a mass there under the square root in the numerator. Just take a careful look at it and then substitute the numbers to get the answer. Again, the same thing with the charge outside the square root and there is a charge inside. So because this can be written as square root times square root q, right? So one of the square roots gets cancelled, and that's how you get the square root q here. And again, this is also square root m times square root m. One of them gets cancelled with this, and you have it in the numerator as a square root. Wow, again a calculation. Okay, so it's actually 1.9 times 10 to the negative 2 meter. That's the radius of the electron. I mean the doubly charged helium atom. The fifth question, a power line carries a current of 95 amperes along the tops of 8.5 meter high poles. What is the magnitude of the magnetic field produced by this wire at the ground? And how does this compare with the Earth's field of about 1/2 Gauss? So you have a power line and it's horizontal. It's carrying a huge current of 95 amperes, obviously, and it's 8.5 meters above the ground. You're asked to find the magnetic field at the ground. So we need to use the formula for magnetic field due to a straight conductor, because obviously the power line is a straight conductor. And the formula you remember the formula for magnetic field due to a straight conductor? And also we are assuming that the line is long and straight, of course. And that's why we can use this formula. B is mu naught times I by 2 pi times r, which is the distance. And mu naught is 4 pi times 10 to the negative 7. Mu naught is called the permeability of free space, and it's always 4 pi times 10 to the negative 7. And r is the distance, which is 8.5. So we get that as 2.2 times 10 to the negative 6 Tesla. And the second part says, how does this compare with the Earth's field of about 1/2 Gauss? Now, 1 Gauss is 10 to the negative 4 Tesla. Now, to find the ratio, it's just B by BH. We already got B here. And 1/2 Gauss is 0.5 times 10 to the negative 4 Tesla. So that's approximately 4% of the Earth's magnetic field. Now the sixth one, a long horizontal wire carries 22 amperes of current due north. What is the net magnetic field 20 centimeter due west of the wire if the Earth's field there points north but downward 37 degrees below the horizontal and has a magnitude 5 times 10 to the negative 5 Tesla? This is a three-dimensional situation here which you have to really visualize, and I can try to draw it on this two-dimensional screen, but you need to try. First of all, it's a horizontal conductor and it's facing north. You're asked to find the magnetic field 20 centimeters to the west. You can have a pen or a pencil pointing due north, and you can pick that point 20 centimeters to the west. It'll be to the left side, because the west is to the left side of the north if you're facing north. You know what I mean? And at that point, now there are two magnetic fields, because you have the Earth's magnetic field there, and the problem says the Earth's magnetic field is pointing north, but down 37 degrees. So can you visualize that? So that's the Earth's magnetic field, and on top of that, you have the magnetic field due to the current in the conductor. And by the right hand rule, if you hold that conductor in your right hand, then you see that to the left side of the conductor, the magnetic field is going to be pointing up, straight up. Okay, kind of this. This is the diagram that you get, and this is the magnetic field due to the current in the conductor pointing up, because the conductor carries a current in this direction. And then at that point you have the Earth's magnetic field pointing 37 degrees below the horizontal, because it says downward 37 degrees. And the blue arrow is the resultant of the two. So you have the magnetic field due to the conductor, the Earth's magnetic field. You have to find the resultant of these two, which is going to be this. How do you find the resultant? You'll have to break this into two components. You will get a vertical component here and a horizontal component. Then you will have to take the resultant of the two vertical components and then use the Pythagorean theorem to find the resultant. Let's go. That's theta. That is you see the notations: magnetic field due to the wire. This is the Earth's magnetic field, and you get the net magnetic field. And by the formula, the magnetic field due to the conductor is mu naught I by 2 pi r. So let's find that. Mu naught is 4 pi times 10 to the negative 7. Current is 22 amperes, and 2 pi times the distance is 20 centimeter, which is 0.2 meter. That gives 2.2 times 10 to the negative 5 Tesla. Now the magnetic field due to the Earth is 5 times 10 to the negative 5. And now I have resolved this along the x-axis. You can see BEX come up. BEX is definitely going to be BE cos 37, because that's the adjacent side, right? Right triangle here, that's the adjacent side. So BE cos 37 gives me 4 times 10 to the negative 5 Tesla. And now this is the vertical component of BE, which is BEY, which is BE sine 37. And I've not written that because I've tried to write the total component along the y-axis, which would be this minus this. Okay, and I told you BEY is BE sine 37. So I've written that in one step. So when you do that, you get minus 0.81 times 10 to the negative 5. You can already see here that this component is bigger than this. That's why the net of the two is negative. And then once you get BEX and BEY, you can find the net by just taking the squares of both, adding them, and taking the square root. So you get bx squared plus bey squared, square root of that. And that gives you, speed that up, okay. When you do all that calculation, get 4.1 times 10 to the minus 5 Tesla. Now that's a really important question to understand, because you have, all things factored into that question. And then to find the angle that the net makes, you got to go tan inverse BEY by BEX. Okay, because that's opposite by adjacent. When you do that, you get 11 degrees below the horizontal. As you can see in this diagram, this net is definitely below the horizontal, so that's the angle that we're getting. Okay, and theta, if you may, was a different angle. Theta was this total angle. But what we found just now was this angle. That makes it very clear, okay? So theta is 11 degrees below the horizontal. In this question, you have a rectangular loop of wire lying in the same plane as a straight wire as shown in the figure. There's a current of 2.5 amperes in both wires. Determine the magnitude and direction of the net force on the loop. Important thing to understand is that this conductor here is 3 centimeters away from the top one, while the bottom one is 5 plus 3, 8 centimeters below. And they're going to be carrying currents in opposite directions. Here the current is going to the right, but in this one the current is going to go to the left, because as the current flows down and then goes to the left. Another thing is that there will be no force acting on the width of this rectangular loop, because the angle between the magnetic field there and the current will be 0 degrees. So there will be no force acting on the width, but here the magnetic field and the current in this conductor are going to be at 90. So what I'm talking about is, you first have to find the magnetic field due to this current at this point. And this current carrying conductor is now kept in that magnetic field produced by this current, right? That's why a force acts on it. And since the currents here are in opposite directions, the forces are also going to be in opposite directions. So when you find the net force, which you're asked to do, you're going to subtract one from the other. And now I've shown you the directions of the forces acting. You see the direction of the force on the top one is up and the bottom one is down. So to find the net, you find the difference, but on the width you see the forces are opposite, so they cancel out. So the net is 0. Now as I explained, the net force is Fa minus Fb, that is the force on A minus force on B. And force is given by this formula. Everything is clear there, because this is the length of A, that's the distance of A, and same thing with B. I can take out the common factor, or the factors in fact, and the length is also common in this case. Both have the same length, so only have 1 over dA minus 1 over dB. You can do this differently by individually calculating the forces and then taking the difference. I've tried to do it in one step. The length is in meters, 10 centimeter in meter, and all the distances are in meters too. Remember that the first one is 3 centimeters below, the second is 8 centimeters below. 3 centimeters and 8 centimeters in meters now. And then you get 2.6 times 10 to the negative 6 newtons towards the conductor. The eighth one, two long wires are oriented so that they are perpendicular to each other. At their closest, they are 20 centimeters apart. And what is the magnitude of the magnetic field at a point midway between them? If the top one carries a current 20 ampere and the bottom one carries 5 ampere. Now look at the situation. That's a conductor carrying a current towards you, because it's a point. The current is coming towards you. This is another conductor carrying a current towards the right. And as you can see, the conductors are kept at right angles. And we are asked to find the magnetic field here. So first you have to use the right hand rule and try to find the direction of the magnetic field due to both currents. Let's do that. Okay, so first field due to the top wire will be towards the right. That's what has come up now. That's when you use the right hand rule, and you got to hold it with the thumb pointing in the direction of the current, which will be towards you. Your closed fingers will certainly be giving you that direction below the conductor. Okay, and then the field due to the bottom wire at that point is out of the plane of the page. Out of the plane of the page, so it'll be directly coming at you. And so now you see that the magnetic fields are at right angles to each other, because one is towards the right, that's the magnetic field due to the top one, and the magnetic field due to the bottom one is coming right at you. So they are at right angles to each other. So to find the net, you got to square them both up, add them, and take the square root. And that's the formula for magnetic field due to a straight conductor. And the T shows top, and the B shows bottom. Okay, and substitute and calculate. I'm taking mu naught by 2 pi r outside because it's common, and it goes outside the square root. Mu naught is 4 pi times 10 to the negative 7, and then 2 pi times the distance. The distance is the same for both, of course, because this is the midpoint, right? It's the midpoint, that's why. And when you calculate that, you get 4.12 times 10 to the negative 5 Tesla. Don't just believe me. Check out your calculations and make sure you understand it. This again is a great problem. Brings us to the last one. It says a single square loop of wire 22 centimeters on a side is placed with its face parallel to the magnetic field between the pole pieces of a large magnet. All right, it's a square loop, and its face is parallel to the magnetic field. And when 6.3 ampere flows in the coil, the torque on it is 0.325 meter Newton. What is the magnetic field? Again, a three-dimensional visualization will help you. The angle between the perpendicular to the loop and the magnetic field. We never take the angle between the plane of the loop. The angle is always taken between the magnetic field and an imagined perpendicular to the plane. And that angle will be 90 degrees. Why? Because the plane is parallel to the field. So if you draw a perpendicular to the plane, that line is going to be at 90 degrees. And The formula for torque is NIAB sine theta. N is the number of turns, I is the current, A is the area. The torque here is 0.325, current is 6.3, and the area is 0.22 squared because it's a square. Sine 90, and when you calculate that, you get 1.07 Tesla. Well, I hope you've enjoyed this explanation, or rather explanations for the 9 problems, and go back over it, look at it, try to understand it, and prepare for whatever examination you are facing. Good luck and thank you.